Hi, in our previous video we talked about filtering images and we use convolution to create different filters. This approach is also known as spatial filtering because we are convolving a kernel over the image. In some applications this can be the simplest solution, but sometimes spatial filtering does not provide the best results. For example, imagine that you are using a radio telescope to get images from a galaxy far, far away, and you know that such telescope is susceptible to atmospherical noise. That noise only affects one part of the image, but depending on the weather conditions, this can change position and size. Then, creating a kernel to clean this data might not be efficient. First, you might not know which kernel will work to remove that noise. Remember that when you apply a filter, you might also lose some valuable data. So you want a solution that only cleans the area that is affected instead of affecting all the image. The good thing is that you notice that the noise has certain pattern that repeats in a similar way every time. For this kind of problem, we can filter the image in the frequency domain. I will start by explaining this in one dimension. The frequency domain deals with patterns that repeat in cycles, such as this pure sinusoidal wave. This wave has a specific frequency f1. Now, imagine that we add some random noise. If the amplitude of the noise is smaller compared to the signal, we will be able to differentiate one from another. However, if the noise amplitude is similar or larger than the signal, then we won't be able to tell which is which. Here is where Fourier will help us. He showed that any signal can be explained as a linear combination of basis functions. These bases are just sinusoidals of different frequencies. Then the Fourier transform can take this noisy signal and decompose it into many different frequencies. In our example, we will obtain something like this. This graph shows in the x-axis a range of frequencies and in the y-axis the power of each one. As you can see, in the frequency domain, it is clear what is the signal. This peak represents the frequency f1, and the rest represent the noise. The noise is a range of frequencies because we made it random, and it has a low power because its values do not follow a temporal pattern. Now, if we want to clear a signal, we just need to define a threshold for the frequency domain and erase all those small components. Then we can use the inverse Fourier transform to get our signal back, and the result will be our original signal. Whatever you call signal or noise really depends on your application. In radio broadcasting, when you tune a radio station, you are actually selecting the frequency that the radio will listen to. But in this case, that signal is just the carrier. Your stereo will erase it and take the noise that was added to the carrier. In that case, the noise can be a pop song. Anyways, on the image, we can apply the same procedure. The only difference is that our signal is two-dimensional. And because our image is discrete, this can be easily achieved using the fast Fourier transform, or FFT. The usual way to see the FFT of an image is something like this. The center of the image are the high frequencies, and as we move to the edges, the values represent the low frequencies. Now, this new representation does not have a spatial correspondence with the original image. In the same way that we saw in a radio example, the FFT sums all signals and sort them according to their frequency. Hence, if we want to apply smoothing to our image, we can just erase the high frequencies and then apply the inverse FFT. Or if we want to detect H's, we can do the opposite. Erasing the low frequencies will result in an H detector. Finally, for our initial example about the galaxy image, if we know that the noise has certain frequency, we will be able to filter only that frequency or a frequency range to remove the noise, regardless if it appears in one part of the image or another, and minimizing the effect that the filter might have in the other values. Okay, in this video we talk about filtering in the frequency domain. We explain the Fourier transform and how to apply the fast Fourier transform and its inverse to perform basic filtering. Okay, see you in the next video.